Hello everyone and welcome to this new episode on my Homebrew Spectrum Analyzer. In this video I'd like to discuss the ADC board, which is really the last block of this whole chain of things that happen to the input signal. In particular, at the end, the log detector here measures the power of the input signal and converts the logarithm of that power into a voltage that is then sent to the ADC board and digitized. It's digitized on that board and then sent to the computer for display and further processing. But before I do that, let me say hello to all the people that subscribed my channel in the meantime, because after I had completed and uploaded the last video, I contacted the people from Dangerous Prototypes and told them that I used their logic analyzer in my video, and it turns out that they posted this on their blog, and then for some reason this also appeared on the website Hackaday, and a ton of people subscribe to my channel, so hello everyone, and I really hope you're going to enjoy what I'm about to show. So, as usual, I'll first look at the schematic, although, to be honest, the schematic is not that interesting, and after that I'll build up the board, and the rest of the video will then be either me debugging the board if it doesn't work, or running a bunch of tests if it works. This is the schematic of the ADC board. There is a power section up here and the actual ADC section down here. And this section is actually replicated. On the right here, there is exactly the same thing yet again. The reason for that is, I actually haven't mentioned that before, but you can build this spectrum analyzer sort of in different levels. And the first level is is a basic spectrum analyzer. The second level adds a tracking generator, and the third level adds a VNA option that allows you to do filter testing and things like that. And in the end, I actually want to build the whole thing, but I'll start with level 1, and hence I will not discuss anything that relates to the VNA right now, because that's actually quite tricky and involves a bit of mathematics that I would like to explain. So for now, I just focus on the bare spectrum analyzer, but these two sections are the same anyway. The power supply section is particularly boring. You get 10 volts in, capacitor, ferrite bead, 2 more capacitors, 5 volts regulator, 2 capacitors. One of the capacitors is 10 microfarads ceramic, and the other one is 100 nanofarad ceramic, and then of course an LED. So there isn't too much of interest here, although I'll come back to that regulator because it's interesting to look at what you can expect and what you cannot expect from a design like that. I want to give you a high-level overview of the ADC section of the schematic before we dive into the details. The ADC chip itself is powered by 5 volts. That's both for the I/O voltage as well as for the main power on pin 2, and the reference is also 5 volts. The input voltage that is measured by the ADC is fed into this SMA connector and then applied to the in plus pin of the ADC. There is also an in-minus pin, although I wouldn't feel comfortable using this ADC as a differential ADC. This looks more like a way to cancel out any offset you've got on your analog ground that you get from maybe some remote site or something. But anyway, this is tied to ground. And on the other side of the chip, there is all your digital stuff. That is a way to tell the chip that it has to sample, as well as means to get the measurement out. Something is interesting about the way the pins are laid out. If you look at the schematic here, on one side of the chip, there is all your digital lines. And on the other side, there is really the analog stuff. So by having a clink up between the two, you're really minimizing any influence the digital stuff might have on your sensitive analog side, where you really want to make sensitive measurements. So that's a pretty nice detail here. But getting back to the schematic. First of all, there is a switch here with two capacitors. And what these capacitors do are, this is actually the video bandwidth of the spectrum analyzer. The lock detector that is connected to this SMA connector here has an output impedance of about 3K or so. And these 3K form RC low-pass filters with these shunt capacitors here, and that sort of smooths out the measurement, and really this is the way how the video bandwidth is implemented. Just by flicking the switch between two different capacitors, you get two different RC time constants, and also let's say two different degrees of smoothing that is applied to the measurement. So you're actually measuring a filtered voltage here. Then note that the 5 volts coming from the regulator are filtered using this 10 ohms resistor as well as a bunch of capacitors. This is really the same we saw in the previous video, where in the DC to DC section of the control board, there was a similar way of really filtering your power supply rail. And of particular interest here is that this is done separately for the reference, again to minimize any digital influence on your reference. The ADC used is an AD7685, which is a 16-bit charge redistribution ADC. And that last part really relates to how it works. Internally, there is a bunch of capacitors that are actually switched in a pretty clever way to eventually shift out the measurement. And I'll link in, if anyone is curious, I'll link in a description of how that works. But anyway, the digital side here, you actually tell the ADC to take a measurement by giving a pulse on that convert pin here. So this is done on the computer, that's going through the control board that we discussed last time, and eventually ends up here. And when the ADC gets this pulse, it takes the measurement, and then you can use this serial clock pin here to shift out the 16 bits of the measurement through this SDO pin here, that is then connected to a transistor that is a pre-biased digital transistor. So there is nothing special to that. It's just that there is like internal bias resistors. I redrew this here. You can see that there is a base resistor and also pull down on the base. If memory serves, these are both 1K. So that just doesn't need external resistors, but other than that, it's a pretty ordinary transistor. And this collector here is then pulled up by the internal pull-up of the PC, and that's how you get your measurement back into the PC. Lastly, let's talk about the reference a little bit here. As you can see, the reference pin is connected through this filter to 5 volts that comes straight from the regulator. Now, what's interesting about this is a 16-bit ADC, which means that you actually can get quite high resolution on this. If you have 16 bits, this means that you have 2 to the power of 16 different codes that you can assign to input voltages. So all the way 0 would be 0 volts in, all the way 0, but 1 on the least significant bit would be, if you do the math, would be around about, I think, 76 point something microvolts. So we're measuring microvolts here. Of course, this is an idealized assumption, but still, the resolution that you get is pretty good. But still, the reference is connected to the regulator here. That is a box standard regulator, and the tolerance on this is, I think, plus or minus 250 millivolts. So even though you've got some good resolution here, you have pretty bad accuracy, because you have no idea where your regulator is actually regulating. In fact, as a minor detail, even though the tolerance on the regulator is pretty high, this doesn't mean that it might jump all over the place. Typically, even though you have a pretty high tolerance on the regulator, this just means that the voltage is going to sit somewhere in that range, and typically it doesn't change too much. Of course, it changes with temperature, and the datasheet actually has a graph on how much this is going to change depending on ambient temperature. But it is far less than the 500 millivolts total range the output could swing between. So once you have this all running, maybe once the system has warmed up, you get a fairly standard output voltage here. And if you use this as a reference, it means that the measurements that you take might be off by some amount, but they will be off consistently. Although if you really want to get a better accuracy on this, of course you use a precision reference and also do all sorts of other tricks to improve on that. But for this spectrum analyzer, it's really not that relevant, because in the end, the way you typically use this is you calibrate your spectrum analyzer, especially if you're testing filters and stuff. Then in the end, you will just have a notion of how much is your filtered output attenuated relative to if there was no filter. And it really doesn't matter what kind of reference you have here, as long as it is stable. So I did a bit of math here, and this just tells you how to really compute the input voltage based on the measurement that you get from the ADC. Remember that as you twiddle with the serial clock line here, you're getting all the bits, the 16 bits that were acquired by the ADC. So if you've got 16 bits, you sort of have 16 boxes where you can write a 0 or 1 in there. And that's where this 2 to the power of 16 comes from, because there is 2 to the power of 16 ways to fill the 16 boxes with zeros and ones. The first one would be all the way 0, and then just everything is 0 and a 1 in the end, and then all the way 0, a 1 and a 0, and so on, until you hit all the way 1s. And if you plug in the decimal value for the measurement that is represented by these boxes into the numerator of this equation, you in the end you just get the voltage, assuming that you know what your reference is. But this is how it works anyway. And I don't think I will go into too much more details on that right now. However, I actually have a separate plan for this ADC board that I will use for something else, and you can rest assured that I'll show this once I got it working and all planned out. So and then we'll have the opportunity to look a little bit more at what kind of signals you get out of the out of that pin and things like that. Okay, that's it for the schematic. Now give me some time to actually build up the board, and then we'll do some measurements. Okay, so I built up the ADC board. Here it is. Although as you can see, I only built one of the two ADC sections and left the second one unpopulated. The reason for that is just that the ADC chip is fairly expensive. I think it's somewhere between $10 and $20. Low quantity at least, and I wouldn't want to waste one of these ADC chips on a board that is clearly that has a major flaw. So I'm going to test it with just one, and if this works fine, then I'm going to build up the second one. That's the control board that I tested last time. So I'm getting 10 volts through these leads, and this is drawing about 1 milliamp right now. And I haven't tested it yet, so I will see whether this works. I'll power it up right now, and because I haven't tested it, as usual, this means that if you see blue light, that's fine, but blue smoke is bad. So let's plug this in, and this is a blue light, so that's fine, and I'm drawing about 2 milliamps, so this seems to be exactly as I would expect. Now I'm going to measure a few voltages, and I can imagine that this is a bit difficult on camera, but I'll try my best. So first I'm going to measure I'm going to measure the 10 volt supply, and I'll use the fence here as ground, and 10 volts should be here. And I get 10 volts, so that is fine. Then I'm going to measure the regulator output, which should be 5 volts. And it's 4.942. So that's exactly what I was talking about before. If you assume that this is 5 volts, but in fact it's 4.9 something, then all your measurements are going to be scaled by that factor. So you have to be at least aware of that and not design it like that if you really care about that kind of accuracy. And then the documentation actually says that I should measure the input of the ADC without anything connected to it. And that should be about 30 millivolts. So I'll try to do that as best as I can on camera. That will be this guy. And that's... give me a second, I think I was touching something. This is going to be extremely high impedance, so of course I'm not supposed to touch it. And this is 0.2 volts and falling. So that's clearly far off the 30 millivolts I should have here. Let me measure that again, because this might also heavily depend on where I put my ground. So let's try and put the ground here. And it's still 100 millivolts. So that is clearly not the way it should be. On the other hand, I'm not really sure what this test is about. There is one more thing I could test actually if I put this on millivolts instead and measure it again. I'm getting something completely else. So the way this ADC works, I don't see how that voltage could be any kind of bias voltage. That wouldn't make any sense. So I guess what I'm measuring here is some sort of leakage. And of course, with these impedances, that is going to be depending hugely on what kind of meter you're using and things like that. So I'm not too concerned about that, and I think that this test is just to see whether you've got your input shorted to either of the rails hard, and that's not the case here. In fact, I could also measure a bit. I measured the 5 volts from the regulator already, but I can also check whether I get these. That's the ground side of the capacitor, and I've got this on millivolts, so let's turn this back. So I'm just checking now whether I've got my 5 volts not just at the output of the regulator, but also on these capacitors, and that is the case. So great. This seems to work fine so far, apart from the wrong measurement. I'm not too concerned about it, although I will run a few more tests on the computer. One thing I will do is I will short out the switch here such that one capacitor is connected to the input, and then use my multimeter to charge and discharge the capacitor while I'm actually measuring using the spectrum analyzer software. And I can do that because the multimeter actually has a pretty high impedance, but it's not infinite. So I'm just connecting one end of the multimeter to the supply, to the 5 volt supply, and the other end to that input, and that should charge that capacitor. And if I connect one end to ground, it should discharge that capacitor. So that is the first test I will do, and then I'll use my signal generator to actually feed in something meaningful in here and see whether I actually get that waveform on the screen. Okay, so I did exactly what I just explained. I connected the ADC board to the control board using the 3 data lines and of course the power that I already had. One data line is to initiate the acquisition, the second one is for the serial clock, and the third one is to feed back the data to the control board and to the computer. Now, the reason this line is actually rising is rising on the screen is because this is my second take at recording this, and I actually already had the capacitor discharged, and now it's charging again to that leakage value or something. So if I connect one end of my multimeter to the input that is still unconnected, although now I have the lower of the two capacitors activated using that switch jumper, and then ground it, it's dropping. It's dropping exponentially, just as you would expect, due to the rules that are inherent to these RC capacitor charging and discharging. Now, if I charge it again, it's rising exponentially, falling, I'm not touching it right now, and rising. So that looks good so far. What I will do next is I will take my signal generator and apply a signal to the input that is properly low, roughly low impedance terminated, just to make sure that I don't have excess ripple on that, and we'll see how that goes. Okay, now I've got my signal generator connected to the ADC board using a short SMA coax pigtail, and I've got it set to a sine wave of 1 volt peak to peak with a DC offset of 1 volt. And that was just to center it here because I was too lazy to change the settings in the program. Now as soon as I turn on the signal generator, I should see a sine wave here. And that is the case. So that seems to work nicely. Although if you look closely, it doesn't happen too often, but it did just as I turned it on. There is sort of weird artifacts as if it wouldn't sample regularly. And the reason for that is, as we saw last time, actually it doesn't sample regularly. And in this case, I don't think it's that big of a deal, because maybe apart from the video bandwidth, you set it to some frequency, then you wait, you measure, you change the frequency, and so on. But for other applications, you'd really want to sample at the regular and defined sampling rate. So this is something to keep in mind for see, now it just happened. And that is not my signal generator, that is just the program sort of stopping and then continuing to sample, but in the meantime, of course, it missed a few samples, so there is that. And as a last test, I will set the signal generator to DC and check the ripple. Okay, I forgot to mention in the test before, the frequency of the sine wave was 1 Hz, so what you saw on screen was actually exactly what I fed into the ADC. And this was just a way of sort of abusing the spectrum analyzer software to get the data and display it to visually verify that everything is working. But anyway, what I have now is I'm feeding 1 volt DC into the ADC, and I'm doing that because in theory I shouldn't measure any change in voltage whatsoever. Now sorry, of course there is noise coming from the signal generator, noise being injected into the ADC, and so on, so that's not going to be the case, but it's actually pretty close. You can display the measurement data using the software, and the MAC data line here is 13,246.47. So it's actually wigging just between one least significant bit. And in fact, if I hold this, it's at 47. Now I rerun it at 46, 47, 46. So this is really good. I'm very happy with that. I was expecting this to be much worse. With all that, I'll do a bit more testing, but in the end, I'm fairly confident that this works reasonably well. And in the next video, I'm going to discuss the lock detector. That one's going to be a bit more interesting than that one. So I hope you stay tuned for that one. And in case you have questions or comments, please post them in the comments below. Otherwise, thank you for watching.